Welcome back. In this lecture we will begin the last module for this course. The last module is module 6 on reaction equilibria. If you recall, in the last module we had explicitly said that we will not consider any reactions, that is to we had situations like that in biological systems plenty, and therefore we could use whatever we developed in that module to explain many situations. But as you all know, reactions take place all the time, whether it is a macro biological systems, for example a bioprocess, there are reactions taking place, or even at the cell level the cell is alive and kicking only because of the thousands of reactions that take place in a cell. And under conditions, under reasonable conditions, we could still consider the cell as a continuum and therefore apply these principles of analysis to the cell also. Therefore the reactions that take place in the cell can also be considered to be a valid system for the application of these principles. So let us start looking at the basis to develop reaction equilibria, the conditions for the same or the criteria for the same. Earlier if you recall in module 5 we had criteria for the phase equilibria, or when there were no reactions that were taking place and so on. We will develop similar criteria when reactions are present. To do that, we will touch upon many things that you may already be somewhat familiar with because of exposure in 11th 12th standards, or even in courses that you took before you are taking this before you took this thermodynamics course. Let us consider a biochemical reaction, say that occurs during a cell metabolism, say a reaction in glycolysis, and let us represent that. This is a hypothetical equation. Let us represent that by 2A plus B giving you 3C. I have just picked up random numbers here, 2A plus B giving you 3C. Let us call that equation 6(1). The stoichiometry represented by the above equation can be written as 0 equals 3C minus 2A minus 1B. I have deliberately written it like this. I have taken 3 to be positive, the product associated coefficient to be positive, minus 2A minus 1B equals 0, or in general I could write the stoichiometry as, or I could represent the reaction as 0 equals sum mu1 m1 plus mu2 m2 plus mu3 m3. In a minute I will tell you what mu's and m's and so on are. In this case mu1 m1, mu2 m2, mu3 m3. Let us call this equation 6(2). I wrote it of this in this form for a reason. I can now make this into a compact notation. 0 equals sum over I mu I mi. This is the reason why I had written it that way. Equation 6(3), where nu I is the stoichiometric coefficient, which we will take as positive for the products of the reaction or the biochemical species on the right hand side of the equation, like this. If this is the equation, on the right hand side, the coefficients on the right hand side we are going to take as positive, and the coefficients on the left hand side, which is that for the reactants, we are going to take as negative. So that works well here. 3C was positive, minus 2A reactant negative, minus 1B reactant negative, and therefore negative for the reactants which are the biochemical species on the left hand side. I have already given you an answer, but why do not you take about 5 minutes and complete it? Why do not you write down mu1, mu2 and mu3 for the reaction that we just saw? Go ahead, take about 5 minutes and write this down. Go ahead, please. Okay. If you had followed the reasoning that we presented earlier, you can easily see that mu1 was the coefficient of A minus 2, mu2 the coefficient of B minus 1, and mu3 the coefficient of C 3, and Mi is the various biochemical species A, B or C in this particular example that is considered in the reaction. Let me state this, although we will not be looking at this in great detail, but it is good to state this here. If there is an inert species that is present in the system, for an inert species that is present in the system but does not react, the stoichiometric coefficient is taken as 0. Okay. Have this in mind whenever it becomes necessary to use this, please use this, and that will make things a lot more general. Now let us go back to what we already know. We know that the changes in the number of moles of each species in a reaction are directly proportional to the corresponding stoichiometric coefficients. What do I mean by that? For example, in the above reaction given by equation 6.1, which is 2A plus 3B equals 3C, if we divide this equation throughout by 2, we get A plus half B equals 3 by 2C, or if 1 mole of A disappears, half a mole of B will also disappear to result in 3 by 2 or 1.5 moles of C. Therefore, the changes in the number of moles of each species are directly proportional to the corresponding stoichiometric coefficients. This particular aspect can be represented as the change in number of moles of 1 delta N1 divided by the stoichiometric coefficient nu1 equals the change in the number of moles of 2 divided by the stoichiometric coefficient 2 equals the change in the number of moles N3 divided by the stoichiometric coefficient 3, and so on, equals delta Ni divided by nu I, and let us say that equals something called delta epsilon. We will call this equation 6.4. Delta Ni, as I said, was the change in the number of moles of a species I, and delta E or epsilon, delta epsilon is the extent of a reaction. It is also called the reaction coordinate, if you recall this term from your earlier courses. Delta epsilon, the reaction coordinate, or epsilon is the reaction coordinate. For a differential change in the number of moles, we can replace these big differences by the differential change, and therefore we can write dN1 by nu1 equals dN2 by nu2 equals dN3 by nu3, and so on, which equals dNi by nu I, and that equals d epsilon. We will call this equation 6.5. And what I would like you to do is now take some time, I will tell you how much time. Look at glycolysis, the various reactions in glycolysis, which is one of the central pathways in the cell. Remember this glucose goes to glucose 6 phosphate, glucose from outside the cell gets inside the cell first, and then goes to glucose 6 phosphate, fructose 6 phosphate, and so on all the way down to pyruvate. Choose that pathway, which is called glycolysis. Each one of those steps, as you know, is catalyzed by an enzyme. Take those individual reactions and write equivalent expressions for, let us say, 5 of those reactions. I am going to give you about 20 minutes to do that. Take about 20 minutes, go back to your biochemistry textbook, biochemistry notes, choose 5 reactions that take place in glycolysis and write this down for improving the comfort level in using this particular equation. Go ahead, please. Okay, now hopefully you would have gotten back the level of comfort that you had in your earlier classes while dealing with stoichiometric coefficients and so on, by writing down the relationships between stoichiometric coefficients for at least 5 reactions in glycolysis. The choice of the reactions were yours. Of course, they were reversible reactions, but that does not matter. Now let us look at the condition for bioreaction equilibrium. Let us consider a system in which the only reaction taking place is equation 6.1, which is 2A plus B giving you 3C. That was the reaction given by 6.1. The Gibbs free energy of the reacting system is GT, as we had seen earlier, that can be written as N1 into mu1, the chemical potential, this is per unit mole mu1, therefore N1 into mu1 will give you the total free energy corresponding to species 1, plus N2 mu2, the total free energy corresponding to species 2, plus N3 mu3, the total free energy corresponding to species 3, or species A, species B, and species C. Excuse me. Let us call this equation 6.6. And now we know from either chemistry courses, the thermodynamics aspects of chemistry courses, or some specific courses that you would have taken earlier, that the equilibrium condition corresponds to a minimum in the Gibbs free energy. Okay, I am just going to take this directly from whatever we know earlier, that a minimum in Gibbs free energy occurs at equilibrium. Since the composition or the number of moles of each species varies as the reaction proceeds, we can think of a certain composition at which the Gibbs free energy is a minimum. The reaction is going to take place. When the reaction takes place with time, the number of moles of each species is going to change, and we already know from earlier that equilibrium occurs when the Gibbs free energy is a minimum. In other words, there must be some combination of moles of these species involved in the reaction at which the Gibbs free energy turns out to be a minimum. That is the whole basis of the argument here. This means that if GT, the total free energy, is plotted as a function of, let us say, N1, the number of moles of species 1, that is the only thing that we can represent on one coordinate, that is the only reason for taking N1. At constant temperature and pressure, a minimum in GT occurs at some value of N1, and that corresponds to the equilibrium condition. if we write it mathematically, at equilibrium dou ni or dou n1 of Gt, the total Gibbs free energy at constant temperature and pressure equals 0. This is just a mathematical statement of the fact that we knew from earlier classes, that the free energy, Gibbs free energy of a system is minimum at equilibrium. Therefore, the slope of the Gt versus N1 curve goes to 0 at that particular point. It is a minimum, and therefore the slope goes to 0, and let us call this equation 6, 7. Further, we know from equation 215 that dGt equals minus St dt plus Vt dP plus sum over I mu I dni. You recall this equation? This equation we have used many times. And if we write equation 215 for our current system of interest, which is the system that consists of that only reaction taking place, we can write dGt, the first two terms of course are minus St dt plus Vt dP, and sum over I mu I dni is plus mu 1 dn1 plus mu 2 dn2 and plus mu 3 dn3. Let us call this equation 6, 8. Now, if we apply 6, 5, equation 6, 5, which is dn1 by mu 1 equals dn2 by mu 2 equals dn3 by mu 3, and so on till and it equals dni by mu I, and we said we could equate it to d of a reaction coordinate, d of epsilon, to a current system. We get dn1 by minus 2 was the stoichiometric coefficient of A, dn2 by minus 1 was the stoichiometric coefficient of B, and since it is a reactant, this becomes minus 1. Similarly, here also 2 was the stoichiometric coefficient of A, and since it is a reactant, by our convention this becomes minus 2, equals dn3 by the stoichiometric coefficient of the product C, and since it is a product, we have a positive terminology here, plus 3. So, dn1 by minus 2 equals dn2 by minus 1 equals dn3 by 3. Let us call this equation 6, 9. And therefore, dGt can be written as minus St dt plus Vt dP plus, remember, this mu 1 dn1 plus mu 2 dn2 plus mu 3 dn3 can be written as mu 1 dn1 is fine, mu 2 dn2 is nothing but minus 1 by minus 2 dn1, that is what we have written here, minus 1 by minus 2 dn1, there is a bracket here and we have taken dn1 common out, and mu 3 dn3 is nothing but in terms of dn1 3 by minus 2 dn1, and that is what we have written here. Let us call this equation 6, 10, and at constant temperature and pressure Gt can be 0. It can be 0 only if the last term is 0, because at constant temperature and pressure, as dt is 0, dP is 0 anyway at constant temperature and pressure. Therefore, dGt can be 0 only if this term goes to 0, and therefore, mu 1 plus half mu 2 must equal 3 by 2 mu 3, or in other words 0 must equal 3 mu 3 minus 2 mu 1 minus mu 2 we will call this equation 611, and which can be compared term by term with the bioreaction stoichiometry as 0 equals 3C minus 2A minus 1B, except that the species are replaced by their chemical potentials. Can you see this here, 3C minus 2A minus 1B, whereas here for the condition of equilibrium we got 3 mu 3 minus 2 mu 1 minus mu 2. Therefore, in general, if there are k species in a bioreaction, written as 0 equals sum over I or k mu I mi, the sum is taken from I equals 1 to k nu I mi, then dgt equals minus st dt plus vt dp plus mu 1 dn1 plus mu 2 dn2 plus so on till mu k dnk. This is where we said that there are k species in the bioreaction, and if we can write this in terms of the reaction coordinate and the stoichiometric coefficients from equation 6.5, we get dgt equals minus st dt plus vt dp plus mu 1, you know this dn1 we could write as nu 1 d epsilon, dn2 we could write as nu 2 d epsilon, and so on, and therefore mu 1 nu 1 plus mu 2 nu 2 and so on plus mu k nu k times d epsilon. I hope you are able to see this. Please go back to equation 6.5 if you are unable to see this. This will drop out from there. The relationship between the various dn's and d epsilon will drop out from there, and from that we will get this expression. We will call this equation 612. Therefore, at constant temperature and pressure, we can write dou epsilon at constant T and P of G equals sum over I nu I mu I. That is equation 613, and we know that GT minimum occurs at equilibrium, and for a minima to occur, the derivative given here must be equal to 0, and therefore the condition for equilibrium is that sum over I nu I mu I equals 0, equation 614, and this happens to be the most fundamental equation to represent chemical equilibrium or equilibrium of a system in which chemical reactions take place. So, please remember this. I think we are almost out of time. Therefore, when we come back in the next class, or let me see whether we can go further a little bit. Okay, if there are independent reactions that occur in a system, for each of those independent reactions there will be an equation of the form 614, that is nu I mu I equals 0. Thus, R such reactions will define the system at equilibrium. Therefore, we will have for a multi reaction system also the condition for equilibrium remains the same, but we will have R such equations that specify the equilibrium. We will stop here, and when we start the next class we will continue with other aspects of reaction equilibrium.